start using those today. And really where we start with is this guy named Gauss, right? He was kind of a Renaissance man, really, really smart, worked in all areas of mathematics and science. Came up with this discovery of the normal distribution along with another statistician. And this really kind of revolutionized how we can approach statistics. In fact, we will primarily be talking about, or at least be around the subject of the normal distribution from here to the end of the course. Now, we'll use it to do different things, but it'll always kind of be there in the background. So we'll make sure we get a really good understanding today and Friday, kind of building those, getting those building blocks of understanding the normal distribution down. So a lot of the times when we think about this normal distribution, sometimes you'll see it referred to as the Gaussian distribution, because this is the guy that came up with it. Another word you'll kind of see for it is the bell curve. So, I've probably drawn it already in this class because I know that we'll be seeing it a lot. All right, it's going to look something like this. We'll talk about why it has the shape it does in a little bit, but for now, getting a little anecdote about this guy who kind of discovered it, right? So when he was young, he was misbehaving, and this teacher says, "Well, I'll keep him preoccupied for a while. Go over in the corner, add the numbers up from 1 to 100." Right? So she thinks it's going to take him a while. He comes back in a matter of seconds and has the correct answer. Right? So as a little child, he was able to kind of come up with this in his head. But if I were going to add up the numbers 1 to 100, so 1 plus 2 is 3, plus 3 is 6. Right, plus 4 is 10. I would kind of continue. Right? That could take you a while. Right? The thing I kind of mentioned last class, right? Maybe it wasn't this section, but right. In mathematics, there's never like necessarily one right way to do things. Right? So there's a lot of ways that are probably the easier way to do things, but there are several approaches. So here, instead of using the method I just explained, what's 1 plus 100? 101. Well, it's 2 plus 99. 101. It's 3 plus 98. 101. That continues until you get down to 50 plus 51. 101. You've got 50 pairs that add up to 101. So 50 times 101 is 5,050. So these are like, different ways of approaching the same problem. I could add the numbers, right? 1 plus 2 is 3, plus 3 is 6. It's going to take me a much longer time. And I'll get to the correct answer, right? But if I can recognize these little patterns, potentially, there's easier ways to do it. So, I don't know, kind of a fun little anecdote. Maybe like, I don't know, bet somebody that you can't add the numbers up from 1 to 100, in a certain amount of time, and you have this method, right? It'll be relatively easy. And really, there's a formula where you can do that with any number starting with 1, going up to whatever number you want. This formula would always kind of give you what that sum would be. Now, we're not necessarily going to use that, so it's kind of a fun way, a story about this guy, to introduce this normal distribution. So, he came up with this normal distribution, and really, it's just a unique example of a continuous random variable. Okay? So the problem is, we already talked about these continuous random variables, the probability of any one value is going to be what? Infinite number of possible values. So the probability of any one value was 0. Right? But we can find the probability over intervals. Think about it this way, like if I have this normal distribution, for now believing that the mean, right, it looks kind of like it's going to be in the middle of this distribution here. What this is telling me is that if I look at intervals of the same size now, right, so unlike a uniform distribution, let's say I look at the probability I'm in between, I don't know, 49 and 50, and down here, the probability I'm in between 9 and 10. I notice the area in between those two values, but under the curve, it's going to be much greater for certain values than it will for others. Right? So we no longer have this uniform distribution. We have a normal distribution. We're seeing values around the mean. It's going to be way more likely for us to see those values, and less likely for us to see values further from the mean. So that's kind of the setup we have. Well, how do I get this curve? Well, just like any other random variable, we have a probability density function. Okay, so we see a lot of variables take on this normal distribution, right? Human height, rainfall, really a lot of biological kind of measures, right? Weight. I'll show you a couple examples today, like human performance typically follows, like in, when I say human performance, usually I think kind of athletics or something like that, but also academically, you look at like IQ tests, they tend to have a normal distribution. So what does that distribution look like? Something like this. Now, don't write this down. We're not going to use this. Right? I mean, we are, but we're going to cheat a little bit. Okay? So this is kind of the function that would give us this normal distribution. So what we would have to do in practice is use this function, which is kind of an interesting to at least look at a little bit because it has those two numbers that pop up a lot, kind of in nature, pi and the natural number e, right? Then the rest of it is really just look at different x values or different outcomes for this x variable, and then everything else is just your mean and your variance. So the normal distribution will be kind of dictated by whatever its mean and variance are. We can have several normal distributions, right? Human height and rainfall are both normally distributed, right? The mean height in inches is much greater than the mean rainfall every year. So the means can be different, but they can still be a normal distribution. We can see different variances and still have a normal distribution. So there's no like rule about exactly how high or how flat this normal distribution has to be. In fact, the only properties we really need for this to be normal distribution is that it follows this probability density function. Depending on the mean and the variance, the shape of it will look a little bit different. Other than the fact that we know, and sorry, here's some labels that we kind of already got those out of the way, the mean, the variance, and those two natural numbers. So what we know is going to end up being true about the normal distribution, no matter what the mean, what the variance is that it will always be symmetric. So if I think about something being symmetric, that means that if I could draw a line down the middle of this distribution, it would perfectly fold on top of itself. So what ends up being true is that the probability of seeing something this far away from the mean or above it, and the probability of seeing something that same distance below it would have to be the same, right? So it's a symmetric distribution, right? Which means the mean will actually end up being equal to the median. We go all the way back when we were talking about skew. We said a normally distributed variable, the mean, the relationship of the mean to the median, they're the same thing. And that's what the normal distribution is. Okay. So it's symmetric, which lets us know the mean is equal to the median. It's going to be defined by the mean and the variance, which we'll kind of break down here for you in just a second. And I think that's all I wanted to say there. So if I have different normal distributions, but one of them has a higher mean, what's that going to do kind of graphically to that distribution? If it has a higher mean, that's just going to shift that distribution to the right. So when we're thinking about different normal distributions, you know, if the mean is lower, shifts to the left. If the mean is higher, we shift that normal distribution to the right. But where we would plot that distribution depends on the mean. So changes in the mean moves that normal distribution along the x-axis. I don't think that's too crazy. What happens if it has a higher variance? Right? So let's say I have two distributions with the same mean, but one of them has a higher variance. So here's my first one. Let's say it's got, I don't know, here's the mean. Let's say the variance is 10. What would happen if instead I have the same, right, same mean, but my second distribution has a much higher variance? So if remember going back, what does the variance tell us? It tells us that the data or the outcomes here are more spread out. Or another way of thinking about this, the variance measured the deviation from the mean. So what it's saying is the higher the variance, the more deviation we see from that mean, which means that values far from the mean, right? Values really far from the mean, are going to be more likely, right? The probability of seeing those values is now higher when we have a higher variance. Right? So these outcomes that are very far from the mean, much more likely for us to see, whereas values near the mean, kind of less likely, right? Less likely for us to see values near the mean, more likely for us to see values further from the mean. If I'm going to kind of connect the dots there, right? We end up with, when we have a higher variance, that will flatten our distribution. Kind of reflecting the fact that it's more likely we see values further from the mean, less likely we see values near that. Any questions on that? So that difference in mean shifts our distribution. Difference in variance kind of flattens, or if it's a lower variance, it would kind of peak that distribution, right? Or make it taller. Thinking about that. So I've got kind of a visual here of that just in the slides, right? Going from 5 to 20, we can see that as the variance goes up, the height of our distribution goes down, or we get a flatter distribution. So if I'm looking at this, right, what can I say about male height relative to female height here? In the relationship to the mean and the variance, I should from this picture be able to tell which of these groups, I guess, is a higher mean, which one has a higher variance. So, which one would have the higher mean? I'm kind of looking at the middle point of this data, right? And here and here. So it looks like men have a little bit higher mean. Now, the first part you said was correct, right? They also have a higher variance, right? Why do we know they have a higher variance? Because, see if we look at this, right? It's a shorter or flatter, or the point that it's at its height on the y-axis is lower. Right? All those things are really just different ways of saying the same thing, right? So this tends to be kind of what we see play out in these normal distributions when it comes to gender, which is kind of, I don't know, interesting that even in different things, women have like higher means, but it tends to be that males have kind of always a higher variance in the distribution, even if we're looking at things like IQ and different biological markers. I don't know enough about science to know why that is. I just know that when you look at that those variables, that's what we tend to see. So we could really do that though with anything, right? We could break down any variable. Think about, maybe we look at kind of comparing countries' average heights or average weights or rainfall or temperature measures, because those all follow normal distributions. We can compare across countries and say which countries have a higher variance in their temperatures or lower variances in their rainfall, or whatever we want to do. Okay, so that's kind of some traits, some qualities, just some talk around that normal distribution. But we're actually going to be able to use that normal distribution to figure out the probability I see certain values. So I might be interested in something like, if I'm choosing a person at random, what's the probability they're taller than, I don't know, 74 inches, right? Well, I can use the fact that that variable is normally distributed to find that probability. Use that probability density function, integrate between whatever values I'm interested in, except for we don't have to do the integration. Someone's already done it for us. We're going to have to kind of work our way to be able to use that work that people have already done. So we know the area under this curve, if it's a or if it's a continuous random variable, has to be equal to 1. Right? So think about the area underneath this normal distribution curve going from the highest to the lowest possible value. I know that area has to be equal to 1. Okay? But if I go out 1 standard deviation below, and 1 standard deviation above that mean, no matter what the mean and standard deviation of that normal distribution are, the probability I'm somewhere within 1 standard deviation above and 1 standard deviation below will always be, what, 68.3% here, if that variable follows a normal distribution. And I'll prove this to you, probably not today, but I definitely will on Friday. So for now, I'm going to take me at my word. Okay? You don't have to have like these values memorized, but it is kind of interesting. So we then start to go 2 standard deviations above and below. Whoops. We're already up to the probability we see something within 2 standard deviations above and below is up to 99 or 95%. And if we go 3 standard deviations, we're up to 99.7%. Right? Like I said, well, I'll prove this to you more in depth next class, but for now, I'm going to take it at my word. But notice this kind of makes sense. As I go out more and more standard deviations, I'm just including more and more possible values for this random variable to take on. So, if the probability I see something between 30 and 40 is 0.3, well, the probability I see something between 20 and 50, a wider range of values, has to be greater than 0.3. And then as I kind of continue to go further and further out, including more and more possible values for this x variable to be equal to, that probability starts approaching 1. Okay? So you kind of think about it here visually as I go further and further out, there's just less area kind of in my tail set. Questions on this? So this is kind of comes out of the fact that it's a normal distribution. we actually are going to write these normal distributions as here's this random variable x, this little like squiggle line here, which kind of means it's distributed normally within whatever mean, whatever variance. Usually those will be numbers like given to us. Now, we have a special case where I've got a standard normal distribution, and that's going to be where I've got some normal distribution where the mean is equal to 0 and the variance is equal to 1. That's what we're going to call our standard normal distribution. Is that my computer? Okay, good. I was going to say, I hope that's not starting now. So we've got a mean 0, variance of 1, which ends up, right? What's our standard deviation then? Standard deviation is the square root of the variance. So the square root of 1 is. So the standard normal distribution has this nice property, which is that the variance and the standard deviation are both equal to 1. It's the only case where that's going to, it's the only situation where that's going to be the case. So now if I think about it, if I saw a value of 1 here, how far away is 1 from the mean? Well, it would be 1 standard deviation away. How far away is 2 from the mean? Well, if the mean is 0, 2 would be 2 standard deviations. And we kind of go on and so on and go through different values like that. So the standard normal distribution makes it, our interpretation of these values a little bit easier. So the goal is going to be to use and exploit the standard normal distribution. Because we've got all these normally distributed variables, but we don't want to do the integration every single time. So if I can convert a regular like normal distribution into a standard normal distribution, someone's already done all the integration for us. You can kind of imagine if we went back to that probability density function, plugging a 0 in for the mean and a variance of 1 simplifies that formula quite a bit, makes it a lot easier to integrate between certain values. So someone's already done all that integration for this standard normal distribution for us, so we have to then think about how do we convert our x variable, this normally distributed variable, into a standard normal distribution. That's our goal. That's what we're kind of where we're going. So what we're going to start doing is instead of calling the values from a standard normal distribution x, for a standard normal distribution, we're going to start calling these z values. And the z values really just tell me the number of standard deviations away we are from that mean of 0. Right? I kind of already alluded to it earlier, but if I had a z-score of 1, well, I know that if I have a standard normal distribution, my standard deviation is equal to 1. So the value of 1 would be 1 standard deviation away from me. And the value of 2 is 2 standard deviations, right? So this interpretation of our z value is really nice for us, right? We can kind of determine how many standard deviations away from the mean. So, what else do I want to say here? I mentioned this. So how do I convert my original variable x into these z-scores? So think about it this way. If I could take a value, let's say we'll do the rainfall, right? So let's say that I want to know what's the probability I get more than 2 inches of rain next month. Well, if I have some different components, if I could turn that into a z-score, and that value of 2 inches of rain ends up being a z-score of, I don't know, 1.3, what we're saying is that that value of 2 inches of rain, that was our original x variable, when I turn it into a z-score of 1.3, that means the value of 2 is 1.3 standard deviations away from whatever the mean rainfall was. So I'm going to take this x variable, transform it into a z-score, and that z-score tells me how far away that original x variable was from the mean. Let me go before we kind of move here. Let me do try to give you another visual of what I'm talking about here. So I'll explain the process by how we do this in just a second. But if I have some variable x, and I don't know, the mean is equal to 50, what I want to do is turn this into a standard normal distribution. So let's say I'm interested in the probability that I see 70 or greater. what I want to do is to be able to determine what that z-score is, or how many standard deviations away from the mean that 70 is. Okay? Let's assume that my standard deviation is 10. Then when I turn that value of 70 into a z-score, I end up with a z-score of what? Yeah, it's the number of standard deviations away from the mean I am. So I'm 20 away from the mean. So I have a z-score of 2. Now that I have this z-score, I can use that standard normal table that I kind of mentioned you should print out to find the probability I see a z-score of 2 or higher from a normally distributed variable. Any questions on that? I haven't explained, there's an easier way. Here with these numbers, it's very easy to see that that value is 2 standard deviations away. But in practice, it's probably going to be a little bit tougher. Right? My standard deviations might be like 8.31. So what's a nice equation that we have to turn these into z-scores? Would be something like this. Right? So we're going to take that original x value we were interested in. Over there was what? 70. We're going to subtract the mean. Our mean was 50. Divide by the standard deviation. And sure enough, we get that same z-score of 2. Right? It's just over there, it was a little bit easier intuitively to think about how many standard deviations away the value of 70 was. Okay? So if I were to convert my x values using this formula, my z-scores will always have a mean of 0 and a variance of 1. So let's think about, go through a quick example here. So here's my original variable x, right? If I subtract the mean from each one of these values, well, first of all, what is the mean? So add these up, divide by 4, I get what? 20 over 4. The mean is equal to 5. So I subtract 5 from each one of these values. So 2 minus 5 is -3, 4 minus 5, -1, 6 minus 5 is 1, 8 minus 5, no, sorry, positive 1, right? And then positive. So all I did there was subtract that mean from each one of those values. When I now find the mean of this new variable, right? I add these up, divide by 4, well, -3 plus -1 plus -4 plus 1 is -3 plus 3 is 0, right? Now I can divide 0 by 4 still, but it's still going to be 0, right? So when I subtract the mean from this x value, my new variable would always have a new mean of 0. I we call that de-meaning a variable. Where essentially all I'm doing is taking that original normal distribution and kind of standardizing the mean so that it shifts that normal distribution back to 0, or that mean of 0. If I then determine what the standard deviation is here, so I go through, right, subtract the mean from each one of these values, square them, and then add them all up. So 2 minus 5 is -3 squared, so that's 9. Deviation from the mean is -1 squared, that's 1. 1 squared is 1. 3 squared is 9. That's all my deviations squared added up. Divide by n. This would give me my variance. So here I end up with what? 20 over 4. I have a nice one where that variance is also 5. So I don't want the variance, I want the standard deviation. So the standard deviation is going to be the square root of 5. Then complete my z-scores. I'm going to take those values where I subtract the mean and then divide them by the standard deviation. So I end up with what? -3 over the square root of 5, -1 over the square root of 5, 1 over the square root of 5, and 3 over the square root of 5. If I then take the deviation of each one of these values from that mean of 0, square those deviations, add them all up, divide by the number of numbers I have, I'll be finding, before we're kind of finding the variance and the standard deviation for that x variable. Now I want to find the variance for that z value. So first z value minus the mean of 0 squared. So basically it would just be that value, right? That value minus 0 is still that value. So if I square that, I end up with what? 9 over 5 plus 1 over 5 plus 1 over 5 plus 9 over 5. I'll square all of these. I add them all up. Divide by the number of numbers that I have. Z that up to 20. 20 over 5 is 4. 4 over 4 is 1. Just kind of a quick, easy example. Sometimes when I tell this to be true, you don't necessarily know why. I mean, other than the fact that kind of I'm in front of the class, why you would necessarily believe me if I don't give you any justification, right? But here's a really quick, easy way we can prove to ourselves with data that if I subtract the mean and divide by the standard deviation, right, my new variable, we're calling it this Z variable, will always have a mean of 0 and a variance of 1. And you can play around with whatever numbers you want to. Maybe if we get to Excel today, I'll give you an example if there's time or on Friday. So now that we have this Z-score, we now know how many standard deviations away that original value for X is from the mean. Excuse me. So if it's positive, it tells me I'm a certain number of standard deviations above the mean. If it's negative, it tells me I'm a certain number of standard deviations below the mean. And our mean, right, will always have a Z-score of 0, right? If I'm converting the mean of my original X variable into a Z-score, it'll always have a Z-score of 0 because, well, if I subtracted the mean from the mean, right, my numerator would always be 0. So, I always kind of like this visual, where if we think about being a certain number of standard deviations away from the mean, this translates into these nice Z-scores. So if I'm 3 standard deviations below the mean, that's a Z-score of -3. If I'm 2 standard deviations above the mean, that's a Z-score of 0. And just another kind of neat, I don't know, I think sometimes it helps to see this. But I think about why also mathematically that works. Let's say my X value is 1.5 standard deviations above the mean. So that in practice, we see a number here. But if that number I knew was 1.5 standard deviations, when I turn it into a Z-score, by subtracting the mean and dividing by that standard deviation, we'll notice that cancels, that cancels. So if I had a value that was 1.5 standard deviations above the mean, sure enough, I'd always end up with a Z-score of 1.5. So we can always map these original values of X onto their Z-scores. So what use are these Z-scores going to be? Well, maybe I want to find the probability of them in between 2 values. So that standard normal table, and I'll pull it up in a second, is basically going to be a cumulative density function for that normal distribution. Okay? So whenever I look a value up in that standard normal distribution, it's going to tell me the probability of seeing that value or anything below it. Right? Cumulative probability. So we had said in our last class, if I wanted to find the probability between 2 numbers, I could take the cumulative density function for the larger value and subtract the cumulative density function for that lower value X. So it's a little bit hard to do the normal distribution, but if we can use a standard normal distribution, someone's already done the work for us. Okay? So let's say I have this value of -1.29. So I had some original value for X. I turned it into a Z-score, which I know would be coming from a standard normal distribution. I have to look up that Z-score of -1.29, and that Z table, or that standard normal table, will tell me the probability I see this value or anything below it, right? Anything to the left. So what does that table look like and how are we going to use it? So I know it's very small, which is why I mentioned it's probably, kind of here's moving out. Make sure you print it out or able to pull a version of it open because it's hard for you guys to see. And I can zoom in, but then we lose like a ton of the table. I'm scrolling around and it's too hard to follow. So just having it in front of you is going to be very beneficial. So notice here, my row headings, right, are going to be the first decimal of whatever my Z value I'm wanting to look up is. So here we had -1.29, right? So the first thing I'm going to look up is -1.2. So we go down right here, right? -1.2. I then use the column headings up there to look up my second decimal place, or the kind of hundredths place, right? So in my hundredths place, I have a 9. So -1.2, and then go over to the 0.09 column. Right? So -1.2, it's almost like you're adding what's on the column, so negative 1.2, except for it's not adding since we're in negative values, but you get the idea, right? It's kind of, you're putting it onto the hundreds place. So negative 1.29, right? Using that column heading. And the probability I see negative 1.29 or anything below it, the table tells me is that 0.0985. That table will always give me that cumulative probability. Okay, so we first look up kind of whatever's in our 10th place, then whatever's in the 100th place, go to where those two, where that row and column would intersect, and that's the probability we see that z-score or anything below it. Or said differently, the probability I see something 1.29 standard deviations below the mean, or even further from the mean. Any questions on this before we keep moving? Okay. So I also have positive z-scores on like the flip side of that table. So one side has all the negative values, one side has all the positive values. So before we kind of go through this one, I want to see if we can get this. So remember this over here. What if I instead wanted the probability that I see a z-score of 1.29 or anything below? So without using the table, just using what we had already done. On that here. So one trait we have in any normal distribution, especially the standard normal, is that it's symmetric, right? So the area to the left of negative 1.29, if I were to like fold this over on top of itself, the area to the left of negative 1.29 is going to be the same as the area to the right of positive 1.29. So we looked that up already over there. Is it 0.0985? So if I want the area to the left of that, it's simply 1 minus that, right? Because I know the area under the curve is 1. So we can exploit the fact that this is a symmetric distribution to kind of, once we look up one value, it might be easier to then already know the, different probabilities. Here, if I knew the probability it's less than or equal to negative 1.29, I automatically know the probability it's greater than a z-score of positive 1.29. And I could use that to find the probability it's less than 1.29. But if I wanted to, I could also just look it up here, right? So I go positive 1.2 all the way over to that 0.09 column. And sure enough, I get 1 minus 0.0985, which is 0.9015. Okay. So kind of different ways of approaching it, right? I can use the table again, or I can use this knowledge of the symmetric distribution to find certain areas. What's going to be true about every z-score that's negative? So if I think about my mean here is 0, every negative z-score, when I look it up in the table, it's going to have a probability less than what value? Yeah. So we said the mean is equal to the median because it's symmetric. So the area to the left and the right of the mean will always be 0.5. So if this, it almost seems like this entire area is 0.5, and I only want to know a much smaller part of that, well, that probably has to be less than 0.5. In fact, as soon as I get a negative z-score, right, the area to the left of that z-score starts to get, below 0.5, closer and closer to 0. If I think about positive z-scores, the area to the left of a positive z-score should always be greater than 0.5, right? Because here, as soon as I get a positive z-score, now the area to the left of it is going to be something that's greater than 0.5. Okay? And sure enough, that plays out in these tables. Notice all these positive z-scores, all these probabilities are above 0.5. We go back to the negative z-scores. All these probabilities are less than 0.5. In fact, if we go to 0.00, we get exactly 0.5 there. Okay? So those tables kind of remind us of that as well. All right. So Any questions on that before we kind of keep moving here? Where are we on time? All right. So we kind of already talked about this. We'll see a lot of z values start to pop up because it's like kind of floating around benchmark values, right? This is really close to 0.9, 0.95, 0.99. So we'll start to see the same z-scores pop up quite a bit. Okay. We kind of already talked about this, right? I can use that complement rule to find that the table always gives me the area to the left of a certain value. So if I want the area to the right, I can't get it directly from the table, but I can look that z-score up in the table, find the area to the left, right, and then subtract from 1. Kind of probably straight. That's not too bad. We already talked about it's symmetric, right? So we'll get out of here a little earlier today. So I'm going to start this up real quick. Trying to get you guys some points for being here today. Dun, dun. It does want to start up for me. Guess I have to restart it here. So let's say I had something like, what's the probability z is greater than or equal to negative 2.53? Okay. Now, if you don't have the table in front of you, you still should be able to probably come up with what this one should be. So if you draw this out, think about you want the probability that you see something greater than that z-score of 2.53. So you can probably just from drawing this out and thinking about what we're doing with the normal distribution, you should be able to determine which of these is the correct answer. Now, if you use the table, the z table, then you definitely can find, a little bit easier. But even just knowing the principles, should be able to come up with what the correct answer here is on this one. Go to the 130 mark. And we'll kind of talk about this a bit. All right, if you haven't gotten answer in, take your best guess. I think I counted 33 or 34, so I'm going to close it out. All right, so what I could have done, if I had that z table in front of me, right, is look up that negative 2.53. So negative, I can get this in the same thing here, negative 2.53. And it tells me that probability is 0.0057, right? But the problem is, if I think about what I'm doing, what I want is the probability it was greater than that z-score. So if I've got this z-score, negative 2.53, I want the probability of seeing that something greater. Right away, I know it has to be greater than what probability? 0.5, right? Because there's the right of the mean would be 0.5. And I think the only other two options up there that were greater than 0.5 were like 0.99 something and 0.5057 or something. Well, the probability of seeing a certain z-value or greater was really close to 0.5. That should mean I should see a value really close to that mean of 0, right? So in order for the area to the right of a z-score to be 0.5, I would have to see a z-score that's really, really close to that mean of 0. So some really small negative z-score, like negative 0.1 or something. Well, I've got negative 2.5, so I can guess the probability is probably going to be a little bit closer to 1, right, than it is to that 0.5. Okay? So if I only have those two options left, 0.99 and 0.50 something, I should choose that value of 0.99. All right, so I had one more thing in the slide. We won't kind of use it as an eye clicker, but you should know how to find it. We just looked up and found the probability that z is less than or equal to negative 2.53. I showed you that was 0.0057. That one should be a little bit easier than the one we're looking for. The probability was greater than that z-score. And then I think I had, just to kind of prove to you, had some data laying around. There's human height, right, from a huge survey data. You can kind of see it's pretty close to a nice normal distribution. Right? Nothing's perfect. This is pretty close. So make sure you get that learn smart done before we show up to class on Friday. We start out with a variable that's not standard normally distributed. Well, the idea behind what we're going to do, keep it as general as possible, is so we've got some variable x, which we know is normally distributed. We might be interested in finding the probability that this variable x takes on a value somewhere in between two different values. We'll call it a and b for now. We'll work through an actual problem where we put numbers to this, but the idea is we're looking for the probability we're in between two values. Right? We've done this with discrete random variables. We can think about with uniform, we've done this. But with a normal distribution, we've got a few more steps, and the first step is going to be that we have to transform this original normally distributed variable into a standard normally distributed variable. Right? So the way that we're going to do this is we've already kind of talked about, we've got these things called z-scores. Right? So the z-score represented the number of standard deviations away from the mean that a certain x value was. Right? So there is some mean here. We don't know what it is. But we can determine, as long as we know what the standard deviation of this variable is, we can determine how many standard deviations away from the mean these two values a and b are. So once we convert these into z-scores, right? These will be actual values, but for now we're just going to write it in general terms. I can use that standard normal table. When I look up this z value, it'll give me the area to the left of that, right? And I'm drawing a circle. It's actually the area under the curve, but I'm just drawing a larger circle to make a point. And then I can look up the second z value, and it'll give me the area to the left of that. Right? Well, if what I wanted was what's in between those two, I could just subtract this smaller area from the larger area, and what I'd be left with is just kind of what's in between those two values. Right? So I can use this idea that that standard normal table is giving me the cumulative probability. So if I find the probability it's less than 10 and the probability it's less than 15, subtract the smaller one from the larger, and I'd be left with just what's in between 10 and 15. Right? So that's kind of the general idea behind what we're doing. So we can break this down into steps, right? If I'm looking for the probability in between any two values, first I want to transform those two values into standard normally distributed, a standard normal distribution, or convert them into z-scores. Right? So I'll just subtract the mean, divide by the standard deviation, and that will turn both of these values into z-scores. Once I have those, I can kind of draw this out and think about what region am I looking for, right? And then after I look these probabilities up, right, I'm then going to have a little bit more work to do, because once I have these two probabilities, I have to subtract the smaller one from the larger one. That's kind of what we call like this last step, right? I might use different areas I looked up in the table to find what I actually want. As we work through more examples, we'll see why this is like a little bit, step 4 isn't always the same, right? It kind of depends on what area we're looking for. So let's work through an example where we have some actual values. This is stapled, so. So maybe
maybe I've got this normally distributed variable. I think it always helps to just draw this out, also to kind of put some limits on, just let us think about where this probability has to be. So I've got a normally distributed variable with a mean of 5 and a variance of 0.5. What would my standard deviation be here? Square root of the variance. So I end up with a standard deviation of 5. I want to know what's the probability I see this random variable x take on a value between 10 and 15. So right away, what do I know this probability has to be less than? So if I think about the area to the right of the mean, that should be a probability of 50% or 0.5, right? The mean for a normal distribution is the same as the median, so it exactly splits this distribution in half. If the area under the curve is 1, then the area to either side of the mean would just be 0.5. So if this entire area is 0.5, I'm clearly looking for something that's going to be much smaller than that. So I know this probability has to be less than 0.5, but other than that, I can't really say much. So the first kind of step that I'm going to do is identify the region, but also turn these values into z-scores, right? So I still want the probability in between these two. I could go ahead and use that z-score equation, right, where I'm going to take the value I'm interested in, x. I'm going to subtract the mean, here is 5, and divide by the standard deviation, which is also 5 here. Now, this gives me a z-score of 1. But even this one was kind of easy given the numbers. I should have been able to know if I remember the interpretation of a z-score. This one would have been a lot easier to find probably without even using the equation. Right? So I think about this. How far away is my value, my x value of 10 from 5? 5 away. If my standard deviation is 5, how many standard deviations away from the mean am I? 1. Now 15 is 10 away from 5. So how many standard deviations away would 15 be? Well, if the standard deviation is 5 and I'm 10 away, I'd be 2 standard deviations, right? So this one was a little bit easier to kind of think about because the numbers were nice and neat. But how many standard deviations away I was, I can almost intuitively figure out, oh, 10 is 1 standard deviation away from me. 15 is 2 standard deviations away from me. Now, when these values get a little bit more, 6.3 and 8.49, obviously we're not going to be able to kind of do that math in our head real quick, and we'll probably have to rely on these equations a little bit more. But ultimately, that's all the equation is doing, right? It's looking at, okay, what's the difference between my x value and the mean, and then to figure out the number of standard deviations that would be, I just divide by whatever my standard deviation is. So once I've turned these into z-scores, I can find the probability I'm to the left, right, of that first z-score 1 by looking up the z-score of 1 in my table. I can then find the probability that I'm less than 2 from that table. If I subtract this smaller area from the larger area, I'd be left with just what's in between these two. So I can go ahead and do that. I'll pull up my standard normal distribution table or my z table. Where is it? Right here. So I got to rotate it. That's annoying. But I go down, find my z-score of 1.00. So we're looking up these kind of integers, right? 1 is 1.00. So that probability is 0.8413. And then I could look up that z-score of 2.00. That probability is 0.9772, right? I'm kind of trying to complete my drawing over here. This area, 0.8413, 0.9772. Now it's just a matter of subtracting that smaller area from the larger area. Any questions kind of over any part of this process?
So, really relying on the standard normal distribution so we don't have to do like the integration of that function between two values makes this a lot easier. So we've got that down, right? This is kind of the slide that goes along with what we just did on the board. Right? So I think I've got, oh, and actually, because I know that I want to use this here in a little bit, and because I ran upstairs and forgot to open this, I'll do that right now. But we'll put like a little bit more difficult numbers in here, and also maybe an example that actually has some relevance and not just kind of a general. We have a variable that has these values. They don't really mean anything to us. So I mentioned last class that a lot of like different things in biology follow normal distribution. So rainfall happens to be one of those things. So we've got this data of Indiana weather back to what, 1890? No. I think it was 1895. Right? So from this data set, I can find the average monthly rainfall, but also the variance of monthly rainfall. And the thing is that rainfall tends to follow pretty close to a nice normal distribution. Right? I think we can break this down by month as well if we wanted to. So I can find June average rainfall and June variance and June rainfall. And even within month, this falls pretty close to normal distribution. Even kind of had the data, I put together a quick histogram. You can kind of see there's a little something weird going on here, but for the most part, right, we get this pretty nice, pretty close to a normal distribution, right? Nothing's usually perfect, but it's pretty close to the normal. Will give us a very, very close approximation to these different probabilities. So in 2012, right, there was this really extreme drought. I was also thinking about like, this was a relevant example. Then I realized this has been quite a while now. But I bring in some more kind of recent years and some of the examples we'll work through. But this year was particularly dry during the summer in different areas of the state. We were kind of in this extreme drought range. And you can even see if we do a timeline, right? So in 2009, kind of February, June, we typically see like a spike in rainfall. This one wasn't that great. You can kind of see in 2010, nice spike in rainfall, 2011. Then we get to 2012, and not only do we not see a spike, it actually kind of like dips down even lower. Right? So kind of not what we expect, kind of out of the convention for kind of the weather patterns in Indiana. And we can actually find out how likely or unlikely it was based off of the historical data that we saw this small amount of rainfall. In fact, I think it was 1.3 inches. So what's the probability that we saw essentially this random variable, which was rainfall, be less than 1.3? Right? That's really what we're trying to find. Okay? So how can we do this? Well, we're going to set up, we know that rainfall is normally distributed. This really is just a matter of converting a normally distributed variable into a standard normal distribution, right? Or kind of convert them into these values in z-scores. So if I've got my random variable x, which is rainfall, I'm told that it's normally distributed, and the mean is 3.4, and my variance is what, 2.57. So sometimes what I would do ahead of time is determine what that standard deviation is. So if anybody wants to help me out, if I take the square root of 2.57, what's my standard deviation? 1.31. Everybody wants to double check that. 1.603. So we've got a standard deviation that's about 1.6. Right? So if we then think about this value of 1.3, the probability of seeing that ranking lower, right? Well, I'm definitely over one standard deviation away from that mean. So I'm starting to get kind of a good distance away. Also, I know that this probability has to be less than what? Yeah, 0.5, because the area to the left of the mean is 0.5. I said last class, any negative z-score is going to have an area that's less than
0.5. Now, the reason why I know this is a negative z-score is because the sign of the z-score tells me what direction of the mean I'm on. If I have a negative z-score, I'd be at a value that's below the mean. For a positive z-score, it would have to be for a value that's above the mean. I can kind of guess what that z-score is. I'm going to just go with 1, but I don't know what the exact value is. These numbers are a little bit harder because I've got decimals going on. So I need to convert this into a z value. So how do I do that? Well, I'll take my x value that I'm interested in, 1.3. I'll subtract the mean, which is 3.4. And I'll divide by the standard deviation, which here, if you didn't find it ahead of time, instead of like plugging in 1.6 or whatever, I could have done the square root of the variance here, right? This would represent my standard deviation. Now that is an actual value. I can go ahead and calculate that ahead of time. But if I wanted to, I can just build it all right into the same formula. If I do this, let's see, I probably did. So this is a weird one where the z-score ended up being pretty close to the x value. That does not necessarily have to be the case. It's just the case here because we're dealing with rainfall, which is, a lower range of 0 to 4. As opposed to, I was looking at income, right? Income amounts are never going to be even close to what the z-scores are, right? Because I could see incomes of 40,000, and that might only be 1 or 2 standard deviations away from me. Even if it's like 10 or 15,000 away, right? Because the standard deviation on the variable of income is much larger. So once I have the z-score, all I do is go to my table, look up negative 1.3, go over the 0.01 column, right? That's the second decimal, and it'll tell me the probability of seeing that z value or anything below it. So if I do that, we have that in front of them. I look up negative 1.3. What do I get here? 0.0951. Now my fourth step is usually I have to take those probabilities and do some work, but here, the probability the table tells me is exactly what I want. So at that point, I really don't have a fourth step there, right? These are going to be kind of the easier ones because when I want the probability of being less than a certain value, well, that's just a cumulative probability. That's what the table is giving me. Okay? So go ahead, look this up. Sure enough, we look up in the table, we'll find 0.0951. What if I had asked what's the probability it's greater, we saw greater than 1.3 rainfall? Maybe like a farmer or something. I know that that's like the minimum threshold. So what's the probability that I'll have enough rainfall for whatever crop I've got, and to have enough, I need at least 1.3 inches. What's the only other difference we would do? Yeah, if we wanted the probability of seeing something above 1.3, then whatever value we find from the table, we just have to subtract it. If we draw this out, kind of the visual, I think helps a lot. Any questions on this? All right, so that's the one that we just worked through. So instead, this was actually last September, so this one's pretty relevant. September 2020. We know that within a month, the rainfall is pretty normally distributed as well. So let's say we're looking at September rainfall, and we've got the mean of 3.25, the variance of 2.37, and I want to know what's the probability I saw rainfall be as low as 0.47. So once again, we're kind of looking for the probability of being less than a certain value. Should look very similar to the one that we just worked through. So I'll give you guys a couple minutes, kind of work on this, talk to the people around you, work with the people around you, and we'll kind of come back together and see if we can figure out some of the parts that might be difficult on these problems. Let me see. I think this is one. I'll write it up on the board. As I say, I think I had an old version. So start working on it. I'll give you some options.
want you to work through this one. And I choose the answer that's closest to what you come up with. If you actually think through this one, you could probably determine which of these. You probably rule a lot of these answers out and determine what the answer is with actually going through the entire thing and looking it up. But I want you to get a little practice kind of working through one of these and trying to come up with the exact answers. Here, of the answers I wrote on the board, choose the one that's closest to whatever answer you find. I might be off to the second or third or fourth decimal point. Go for another 30 seconds here. All right, you haven't gotten an answer in, take your best guess here. Thought I counted a few more than 25, so I'm gonna close it out. You get everybody in here? All right, I think I counted 29. All right. So, first of all, what should this probability be less than? Which of those answers can you rule out right away? C, D, Y. Think about what we got here. We've got this variable that has a mean of 3.25. Variance is what, 2.83, 2.37? So what's my standard deviation? Approximately, everybody find it? 1.5? 3 or something. So we want to know what's the probability we saw 0.47 inches of rainfall or anything less. So right away, we know the area to the left of the mean is 0.5, so our probability should be quite a bit smaller than that. Right? Now, just because we're like, 3 inches away from the mean, doesn't necessarily mean we're that many standard deviations, right? The standard deviation was 20, being 3 away isn't actually being that far, right? For the standard deviation of 1.5, and if I rough, like I'm grossly rounding here, but I'm close to 3 inches away, which would be approximately 2 standard deviations. Now we're probably not real familiar yet with kind of different z-scores or exactly what makes us kind of have a value that's far from the mean. But anytime we see something more than 2 or 3 standard deviations away from the mean, that's pretty unlikely. Or said differently, right? If I end up with a z-score that's approximately 2, I'm pretty far away from that mean of 0. And the area to the left of my z-score is going to be pretty close to 0, like pretty small. So if I'm guessing over there, I'm probably going to guess A over B.
because A is a lot closer to 0 than it is to 0.5. In fact, if I did have something where the probability of seeing that value or anything below it was 0.4, whatever I wrote over there, 0.47, it would have to be a z-score that's just barely below 0, right? Probably something like -0.2, maybe -0.1, right? We end up with a z-score that's going to be pretty close to, and I put approximately 2 here, approximately -2. Right? We're going to be about 2 standard deviations below. So we actually calculate that z-score. What is anyone get off of that? Going back to the step of -1.81 should be what that is. How did you come up with that? You just took that value x that you're interested in, 0.47. You subtracted the mean of what? 3.25. And then you divide by your standard deviation, which I asked you for earlier. We go ahead and put those values in. We should get about -1.81. So I was rounding very inappropriate earlier. So I said it was about -2, right? It's a little bit lower, right? -1.81. If I go ahead and look that value up in the table, what's the area to the left of the z-score of -1.81? Oh, that was close, right? So kind of the answer closest to that up there would be 0.0351. Right? I knew it was going to be somewhere around 0.03. Now, knowing you, right, I have seen this enough that I could kind of recall that from memory. You probably can't yet up to this point, right? So -1.81, if we go to this table, the way we look that up is -1.8. And then the column that has our 0.01 is this second column. So sure enough, 0.03. Actually, someone lied to me. It is 0.0351, right? Who lied to me? So, right, so this actually is yeah, I thought I was actually like, yeah, I thought I remember that, right? So we got 0.0351. That was the area we were looking for, just the area to the left. So we don't really have a fourth step. Okay. Any questions on that one? Okay with this? One thing I want to point out here, because I had people ask me this. So like, I'm starting to say things like, you know, being 2 or 3 standard deviations away from the mean is very unlikely. So that probability starts to get really small once they start looking at z-scores that are like -2, -2.3. In fact, notice, I mean, once I get to like -2.4, the area to the left of that is already less than 1%. I'm at 0.0082 already when I'm just 2.3 standard deviations away. So anytime I go past 2 standard deviations away from the mean, I'll have a z-score of 2 or more, or -2 or less, I guess, right? A larger negative value. My probability starts to get really small. In fact, if we go to 4 standard deviations away, -3.9, I don't even have anything out until like the 5th or 6th decimal point. Right, so I'm pretty much at a probability of 0. If I see something 4 standard deviations away from the mean, I mean, the likelihood of seeing that, the probability is like less than 0.001%, right? We're getting really, really unlikely events there. So the values in between 0 and 2 are a little bit harder to kind of visualize, but as soon as I get past 2 standard deviations, I should know the probability of seeing something that far away from the mean is really small. All right, so I already kind of have this drawn up on the board, all right? But once we found that probability from the table, that's exactly what we wanted to do. So I had some things in here. I didn't know how quickly we'll get through this. I'll probably say this for the end. I think we're gonna jump into Excel for a little bit today, just so we get a glimpse as to how we would do this, not just by hand, but how can we do this in Excel, right? So one of the problems with that table was we can only go to 2 decimals. Another problem with that table, so if I wanted to go to the 3rd decimal, I'd almost need like a 3-dimensional chart and then be able to look up the 3rd decimal on the z-axis. Or I'd actually have to integrate that function myself. I don't want to do that. So I've got this Indiana weather data file. That should be under the in-class data folder on Canvas. So it's not blank. It has kind of all this work in here. I'm going to, actually, this is not the one that
you would see. Let me see. I had oh, there's one I didn't save. Let's see if it's this one. I think it is. Yep. Sorry, it should look something like this if you go to that temp-normal sheet, right? So we have a bunch of worksheets down here. Some of it was like, I think I created the time series graph somewhere on this one. Maybe it was here. Here it is. Yeah, right. Then I've got rain. But we're going to use this temperature one, right? So not only does rainfall follow a normal distribution, temperature is pretty close to a normal distribution as well. So what I have here is every single month in Indiana for every year, whatever the average temperature was that month. Right? And I think this is a little different in the slides because I think I have, yeah, I've got some newer data here. Okay. So I go up here, and if I wanted to find the overall, right, kind of start labeling this. I'll get out of here. Let's go to view, zoom, so we can see this a little better. Right. So this first row, I calculated the mean, the variance, and the standard deviation. Right? Won't really review that. It's pretty easy, right? All I did was use my average function to find the average temperature in every year, the variance, and I kind of did this a little tricky way. You didn't have to use the annual. You could just select all these. Don't worry too much about that. And then to get the standard deviation, I would just take the square root. But if I wanted to break this down by month, notice I could take the average of the column that has June temperature. That would give me my mean June temperature. Take the variance of that June temperature column. It gives me the variance on June temperature. And then just take the square root of the variance to give me my standard deviation. If I wanted to, I could use that built-in standard deviation function as well. It should give me the same value. Okay. So I did this for 3 different months, right? June, July, and September, right? And I'm actually going to use this value for all of them here, just to give us an idea about what's happening. Okay. So I'm going to delete this real quick and kind of rebuild it for you. So we're going to kind of start off with the same cutoff value. So the first thing that we're going to try to do is find the probability that this June we see an average temperature of 71.4 or lower. Okay. So we know that if we're doing this by hand, we would turn this into a z-score, then look that z-score up on the table, right? And because we wanted the area to the left, that's what the table told us, we'd be done. Right? So we're going to use Excel just to do some math for us first. Okay. It's not going to be a built-in function. We're just going to do math. How do we calculate the z-score? Well, I'm going to take the x value I'm interested in finding the probability of being less than, right, 71.4. Subtract the mean for June temperature, and then divide by the standard deviation of June temperature. Now, if I do this, why is this going to be a problem? I just got a z-score of 43. That doesn't seem quite right, right? I'm looking at a value that's not very far from the mean. So what did I do wrong here? Yeah, right. So a lot of the stuff that we're going to be doing moving forward, we're going to do some of our math in Excel, like, not a built-in function, but just typing in a formula. We have to be really, Excel doesn't recognize order of operations errors because it doesn't know exactly what you want it to do. So we have to be really careful about how we're entering in equations when we're doing math in Excel to make sure that we know that order of operations is working correctly, right? Often that's just throwing in some parentheses, okay? So now we're going to find the difference between our cutoff value and the mean, and then we're going to take that difference and divide it by the standard deviation. So that's what we wanted to do. So we end up with a z-score of 0.21, right? So it's only about 0.2 standard deviations away from the mean, okay? Now, if I copy this across, it's going to update everything. So I'll be using the next cutoff value for that month, but it's going to update my mean and my standard deviation to then be looking at July. So if I drag this across here, we start getting different z-scores. And this kind of makes sense, right? If we look at these 3 months, July has the highest. And I think I did September here. Did I do September? This is not September. I have this labeled wrong. This is August. I forgot a month there. So if I look at the average temperature in July, it's the highest in Indiana. So I know that seeing 71.4 in July, well, that's something below the mean, right? In fact, it's quite about 1.5 standard deviations below the mean. So it's going to be less likely I see the average temperature be 71.4 or lower in July than it would be in June, right? And that's because June has a much lower average, right? 71.4 in June would actually be something that's above the average temperature, right? But I can find the probability in each one of these months that I see that average temperature of 71.4. So how can I do that? Well, I've got my z-score. I now use this built-in function called norm.s.dist, right? So what this function does is essentially what we were doing with the table. That's what this function does. It looks up a z-score and it looks like basically looks up in the table for you and then tells you what probability you would have found. Now what it's actually doing, remember those tables, all those probabilities come from integrating that function from negative infinity up to whatever that z-score is. So really what Excel is doing is it's doing that integration behind the scenes. But if it's easier to think about, it's basically just looking up that z-score in the table for you, okay? So I tell it the z-score that I want it to look up, and then we're always gonna say comma 1 here. So this is cumulative, right? The tables were always giving us cumulative probabilities, so we're always gonna put a 1 in there. If you put a 0 in, I don't know, it does some goofy thing in Excel where like, if I didn't make this cumulative, what should the probability of any one value actually be? 0. So what it does is it's not really not making it cumulative. It's looking over like a certain interval based off of the kind of, looking at like an infinitesimally small interval. So, but we're never going to use it. It doesn't really have any practical use for us. So we're always going to put comma 1 here, which means that this function works just like you would looking up the z value in the table. Okay? So sure enough, 0.21, if I were to look that value up, myself in the table. So I go down here. If I had a z-score of 0.21, 0.5832, 0.5849. Well, notice this can get a little more exact because it's not constrained to 2 decimals. It didn't have to round the z-score and look up 0.21. It could actually use this value and then integrate the function. So in Excel, we can be a little bit more exact. All right, so that's kind of helpful. Any questions kind of up to this point? All right, so we're just using that, norm.s tells Excel use a standard normal distribution. Then you just tell it your z-score, and then comma 1 to give you the area to the left of that z-score. Okay. And I could copy this over, right? You can kind of think about the probability that the average temperature in July is 71.4 becomes less likely because, right, now, the average temperature in July is a little bit higher. So seeing 71.4 isn't near as likely. And then as the temperature kind of falls back down, the average temperature in August is a little bit lower. Well, now seeing the average temperature of 71.4 lower becomes a little bit more likely. So it's kind of those probabilities or how we would find those probabilities for the standard normal distribution in Excel. Okay. Any questions on that? So what if I wanted to find the probability of being above a certain z-score? How could I use that norm.s.dist but find the probability of being above a certain z-score? Simply, yeah, right? This is where if I've got the area to the left, if I want to be greater than something, I want the area to the right, it would just be 1 minus that. Right? So that would copy that over. Now I've got kind of the probability of seeing an average temperature above that cutoff point for each month. Any questions on that? It shouldn't be too bad. So we have another function that makes life even easier, right? So we've got this norm.dist function. So sometimes we might want to see what that z-score is, right? We might just be interested in how many standard deviations away from the mean that we are. Sometimes we don't care. Ultimately, what we want is just the probability, right? So the norm.dist, what it will do is you tell it the cutoff value you're interested in, x, comma, what is the mean of the variable that you're looking at? So that's up here, comma, the standard deviation of June temperature. And then just like norm.s.dist, comma 1 is the last thing, tells it to make it cumulative. So what this function does is it basically calculates the z-score for you behind the scenes. It has the 3 components it needs to calculate the z-score, so it does that for you behind the scenes, then looks it up in that standard normal table, and returns you the probability of seeing that z-score or anything below it. Now remember, when we're saying things like what's the probability I see this z-score or anything below it, what we're really saying is what's the likelihood that I saw a value that was this many standard deviations away from the mean or anything even further from the mean. So even though we're looking up the z-score, it really relates back to whatever that original value we were interested in was. So here, we don't even have to worry about even thinking about the z-score because we're just going to put in the value and say, okay, I know that Excel's going to turn this into a z-score and tell me the probability of seeing something that many standard deviations away from the mean or even further. But ultimately, really how I want to translate that, it's a probability of seeing 0.47 inches of rainfall or anything less, or a temperature of 71.4 or anything less than that, right? So we have to use these z-scores as kind of an intermediate step, but ultimately these probabilities speak to whatever that original variable x was. So here, it's going to be the probability that in June, we see average temperature be 71.4 or less, right? So we hit enter here. Sure enough, we get the exact same thing that we found before. And I could copy this over, and I'm getting the exact same probabilities as I did before. I just have a little bit less work. I don't have to calculate the z-score. Excel does it behind the scenes for me. The only issue with this is if I ever want the z-score, well, you know, this function kind of keeps it, doesn't like store it anywhere where I can look at it. Okay. Any questions over anything there? So the first part of that Excel assignment that I'll get up there will kind of look similar to that, where you'll just be given a variable. You'll be told what the mean and the standard deviation is. Or actually, sorry, I probably won't tell you the mean. I will give you the data. You will then calculate using the average and the variance functions in Excel, figure out what the mean and the variance are, and then start to find the probability of seeing, you know, different values, maybe below certain values, above certain values, between two values, right? So if I wanted to find the probability of being between two values, it's just like we did it by hand. I would look up, you know, use that norm.dist to find the probability of being less than, say, 10. Then I would use norm.dist to find the probability of being less than 15 and subtract that smaller probability from the larger one. And that would give me the probability of being in between those two values. So just think of, you can do anything by, you know, in Excel that we were doing by hand. Whereas when you look up those values in the table, now you just have to use that norm.s.dist or norm.dist. Depending on if you want to calculate the z-scores or not. Okay. All right, so I'm going to end today with, you know, I told you that these, I don't remember if I showed you this at the end of the last class, right? We kind of talked about the normal distribution pops up a lot, and that's why it's so valuable. So I had some survey data where people responded what their height was. If you graph it out, and I can't remember, I probably excluded one gender here so that I didn't get a bimodal distribution. But right, if I just kind of had one of them, I can graph out height, and it looks pretty close to a normal distribution. I mean, it's a little off here and there, but pretty good, right? Pretty close approximation. I also I didn't show you this before, did I? No. Okay. I also geeked out one day on Instagram, so I saw this. I think this was like a this is like a CrossFit thing, so some workout, and I forget what the caption was. I should have said the whole thing was like, "Are you in the 99th percentile?" And it was probably like trying to get people to be excited about how well they did relative to everybody else. But when I saw it, I was just like, "This is maybe the coolest." This red. So what is red was women, right? The performance of women at whatever workout this was. I mean, I couldn't draw a normal distribution that looks better than this, right? So human performance, when we look at this a lot, really close to a normal distribution. The men was close too, but it had a little bit of a weird thing going on here in this one range. Like we see it pop up all over the place, right? So I had this old data set laying around, and I think this speaks to, you know, it's a normal distribution example, but it also is, I don't know, maybe a good lesson to learn about statistics. So I had this data set, and it was like all these powerlifting meets across the United States, like all these, like every single age was represented. So I kind of cleaned it up, and then I just said, okay, I'll choose one of the lists of these powerlifting meets, which was the deadlift, and I'll kind of look at the distribution. So pretty close to normally distributed for both males and females. There's a little bit of like a longer right tail, but that's pretty easy to describe.
Because the left tail here, so people who wouldn't have lifted as much, are probably people who like just don't go to compete, right? The people who are going to go compete are probably the ones who are maybe lifting more. So you're always going to have the right side of the distribution a little more overrepresented. If I could like force every single person to compete, well, then I would probably have built out a real nice, a little more of the left side of the distribution, and this would be pretty close to normal distribution. So, you can have this data and someone tells you, well, look, I mean, if I try to find like the average male weight lifted, it's, about 600. Look at females, it's about, 300. So, men are way stronger than women, right? But I mean, this is like asinine, right? So if you look at this data set, you just take a second and think, okay, why might there be such a discrepancy in the mean? I can tell you there was a lot more 400-pound men in that data set than there were 400-pound women. Like there was, so right away you should be thinking about, we've got a very vast difference in the average weight, right? Which someone's weight is probably going to greatly influence how strong or how much they can lift. So I always had this idea that if you could like get two individuals, male, female, who had the exact same height, exact same amount of muscle fibers, there is no biological reason why that male would be any stronger than the female if they had the exact same amount of muscle fibers. So I was like, well, we can at least account for just one of these things, right? I can't account for height in this data set, but I've got every single person's weight. So there's a thing you can do, think about it almost like, I'm going to take the total amount lifted and then just divide it by that person's weight. So now I'm getting this measure of like per pound of body weight, how much does this person lift? So this is something that in the Power they call a Wilks score. So this is in the data set. So basically it tries to like factor in the weight with everybody. Now if I graph these two things out, still a really nice normal distribution, which is pretty cool. But I try to find like the average here. It looks like it's just below 400. I'm trying to find the average here. Looks like it's just below 400. I think there was a little bit of a difference in those two, but there's some tests you can run that are kind of outside the scope of this class. And you actually find that statistically, there's no significant difference between the averages of these two, right? So that if you just factor in one thing, which is body weight, there's actually no difference in kind of per pound strength of men and women, right? So I don't know, I thought it was kind of nice because you've got a bunch of normal distributions, but it also kind of highlights that we can't factor in some of these things that might differ between groups. It leads us to wildly incorrect conclusions. Well, if we can start to factor in some of those differences, we can actually get at what the actual answer to the question is. And once we get to like regression, we'll talk about we're actually able to factor in not just one factor, but several factors we can control for. So this is kind of alluding to that. So